As we continue looking at integrated rate laws, we can use experimental data to determine both the reaction order and the rate constant. So to remind ourselves, we have a zero order, a first order, and a second order rate law expression shown here, where the y-axis is either concentration, the natural log of the concentration, or 1 over the concentration, and that is graphed against time. And so how could we tell what the reaction order is from experimental data? That is a great question. So if we look on the left side of the slide, we can see some data. And so we are able to detect the concentration of the substance as a function of time. So as the time goes on, more and more of the substance is becoming reacting or disappearing for some reason, either electrochemical or some other means. And so how do I know, is this a zero order reaction, meaning it only depends on the rate constant, or is it first order or second order in respect to A? Well, the best way to do this is to graph it, because we can tell that if we graph a zero order reaction and it has a negative slope that is linear, it could very well be zero order. Whereas first order and second order are going to have different graphs, but if they have a linear slope, then they may be first order or second order. And so basically the question is, how do I tell what the reaction order is from experimental data? The best way to do this is to graph it. So let's look a little closer. I'm going to open up Excel and we are going to graph this data that you see here on the bottom left-hand corner, and we're going to see what happens. So here is that data that you saw on our bottom left-hand side of the screen. This column here is concentration of A. This column is natural log. So I can just type in equals ln. So I can type in equals just to show you how it works, ln, and then either you can select this function by double clicking, and then you go and you choose the cell you want to take the natural log of. And you'll notice if you were to plug this into your calculator, you would get the same value. So if you were to type in equals ln of 8, you would get 2.079. And then I can drag my cells down to populate it for my entire column like that. Same thing here, is if all of these weren't filled in and I were to type in equals 1 divided by my concentration of A, which is 8, I'm going to get the 0.125. And then I can drag this down, and what that does is it makes it so every single cell is 1 divided by the concentration for that moment in time. And so now I have come up with the data for all of my possibilities. What do I mean by all of my possibilities? Well, either time versus concentration, time versus the natural log of concentration, or time versus 1 over your concentration. And so that's going to tell me whether or not I have a zero order, a first order, or a second order. And so by doing this, this is my data, and now I just have to graph it. So I can graph these two, and I've done this, I've color-coded them to try and simplify things a little bit easier for us. This first column is the kind of yellowish orange, and that's a zero order graph. Blue is first order, so it's time versus the natural log of A. And then my second order graph is this green one, and that is 1 over A, and then time on the x-axis. So I've got all these graphs. How do I know from my graph now what order it is? Well, they each have what's called a trend line shown. So remember, that's your y equals your m, x plus your b, your intercept. They all have those attributes about them. But then they also have an r-squared value. Now your r-squared value does not tell you how good your data is. It just tells you how closely you can represent your data points with a line. So it doesn't tell you if the data is good or bad. It simply tells you whether or not it is linear. So whenever we are working with these reaction rate data, what we can do is we can say the order that is most linear is going to be the order that best represents the data. I will say that again. Whichever of my graphs is most linear is going to be the order that best represents my data. So what that means is that for this set of data here, I can most accurately graph it as a line if I graph time versus the natural log of A. How do I know that? It's got my r-squared value closest to 1. Whichever graph has my r-squared value closest to 1, that's going to be my order. So for this data, it's not 0. Notice how the data kind of curves when you graph it, A versus time. And so that's not linear. It doesn't look like it follows that line very well. Same thing for a second order. When I graph 1 over A versus time, see how it kind of curves out and then back up? And so it's not a second order, because if it were second order, it would form a line. But this graph, that looks fantastic. The line and the trend line are all 1. And so therefore my graph is first order. So if I were to ask the question, is this data 0 first or second order? We would say first order. And so that means that my integrated rate law for this reaction is going to be this. I would replace my A with whatever component I am measuring. So whether it be nitric acid or nitrogen monoxide, it doesn't matter. Whatever the sample is, and if it's dependent upon that, you would replace the A with whatever the chemical formula is of that compound. So here is my equation. I know it's first order, so I've determined that. But what about the rate constant? Remember that y equals mx plus b. That means this is my b, my t is my x, this whole thing, natural log of a, is equal to y, and then negative k is my slope. Notice here, it's a negative slope. So that means it's going from top to bottom right. If it had a positive slope, it would be going in this direction, but it does not. And that's because I expect it to be negative. So in this equation, whatever my slope is equals negative k. So my slope is negative 0.6672. I found that by just looking here in my trend line and finding the value. That equals negative k. So then what is my k value? K equals 0.6672. But I need some units. I can't forget those. So if this is first order, that means my rate equals my k times my concentration of my A to the first. So if my rate, remember how we did this, is molarity per second, then my concentration here is molarity, so that means my k is 1 over second. And so my units here is s minus 1, and that's my k value. And so here I was able to go from experimental data to determining the reaction order of the data and then determining the rate constant. Let's do 3 more examples of this. Here is another set of data. It is a different data, and so it's going to be based upon a different reaction. Now, if we graph it the same way. We've got concentration of A, natural log of A, 1 over A, all of my formulas I have already set up for you. But now I look at my graph, and I can see here we've got an r squared of 1. You can't get much better than that. But my first order graph was actually pretty good. It doesn't look bad at all. 0.999 is, 0.9901, that's really close to 1. So that looks good too. And then my second order is actually not bad either. You can't see the huge curves that we were able to see on the last set of data. But still, you're asking the question, what trend line best matches my data? And that is whatever r squared value is closest to 1. So that means that this is a 0 order data, 0 order reaction, because it has the r squared equal to 1. And so I can go back and I can look at this data. I know it's a 0 order graph, and so it follows this integrated rate law. And I can then use this integrated rate law in order to determine the rate constant. So how do I do that? Remember, my y equals my m, negative 0.667. That's my slope, x, and then plus my intercept, so 7.9988. Now something to note, A0, what does that mean? That's my concentration of my analyte at time 0. And so it would have been around 8 molar. So that's how much I started with. And if I look back here at my Excel spreadsheet, hey, look, that's exactly what it is. And so you can see how they're very closely linked. Yes, there's a little error, but there's always a little bit of error whenever you're trying to make experimental data match a mathematical model. What then is my K? Well, my K, once again, we've got your slope equal to negative K. My slope is 0.6667. Throw an extra 6 up here, equals negative K. So therefore my K equals 0.6667. What are my units? It is 0 order, so my rate equals K. My rate is molarity per second. That equals my K. So what does my units need to be for K? Molarity per second. So M times S minus 1. And that is my rate constant. Let's do another example. So here's another set of data. Same process as before. I've got my data. I took the natural log of these two columns, or of this column. I took 1 over this column, got my data, and then graphed it. So here's my 0 order graph. Notice how it's curved, doesn't really fit the trend line of a 1 very well. Here, perfect, r squared of 1. Here, nope, doesn't really match. It's got a curve to it, so it's not very linear. And so this would tell me that I have a first order set of data. So how do I then find the rate constant for this data? I remind myself that it's first order, therefore it follows this formula. I can then go forward and say my negative K equals my slope. So slope equals negative K. Negative 0.0069 equals negative K. K equals 0.0069. What are my units? Rate equals K, concentration of A to the first because it's first order. Molarity per second. My K, this is molarity, therefore it is 1 over second. You can either do it mathematically or you can memorize that. I prefer to do it mathematically. Now for our final example. Same setup as before. You've got your concentration, natural log of concentration, and 1 over concentration. Here you've got your 0 order. See how poorly that fits a linear trend line? Not at all. R squared value of 0.588. Also not great for first order, but here we go. Second order graph, very nice fit to a trend line that's linear. So we've got r squared equals 0.9999. We come back over here and we ask ourselves, what is the rate constant? Because it's second order, we need to use this equation. But once again, your K equals your slope. And so you've got M equals K. Notice how my slope now is positive, but also in this equation, my K is positive. So that's my unit for K, but what are my units? So if rate equals K times my concentration to the second because it's second ordered, molarity per second equals something times molarity squared. Therefore, I need to get rid of one of my molarities in order to have molarity per second on this side. So that means it is M minus 1, S minus 1. Or you can write it as 11.955 times 1 over MS. Either way is fine. It's the same thing. So with that, I hope you know that you can now look at graphs for different orders and be able to predict what is the order for experimental data. Just going from a set of experimental data of time versus concentration, mathematically determining the natural log of your concentration and 1 over your concentration, graph the data, and then look at that trend line to figure out if a reaction is 0, first, or second order.